Greetings everybody, welcome to the latest edition of the Physics Corner, a series of videos where we introduce and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today is the second part of a two-parter on resistor circuits. In this particular episode, what we're going to do is take three resistors in a mix of series and parallel configurations and show how to solve for the effective resistance, the current not only through the battery but also every individual resistor, and the power that is both supplied by the battery and used by the individual resistors, and compare the totals. So let's begin. So in this particular problem, we have three resistors in this configuration. Resistor 1 here, then there's a junction where we split off to a second resistor here and a third resistor here. Those wires come back to a new junction, connect right over here, and then not pictured but understood is a battery that completes the circuit. So as I've done in previous videos, I'm showing just the resistors to emphasize their role in this, but this does complete a full circuit. So let's go ahead and get that started on solving. So when you're dealing with a series of resistors, or for that matter, capacitors or other various kinds of circuits, you want to simplify it, simplify it, simplify it. Make it until you can get to one resistor and just the battery, and that's it. Now, there are circuits that are far more complicated that you can't use that particular system with. That is perhaps a different video. But in this particular video, we can actually do this. So, how do we simplify? Well, we're going to take this picture here, and if you look, these two resistors here are in parallel. So, that's an easy sort of pair to talk about. On the other hand, if you were to ask in series, this resistor is in series with both of them, but do you use this resistor in series with this, or this resistor in series with that one? Well, that's kind of hard to figure out. But if we simplify this pair of resistors that are in parallel right now first, then we can talk about this resistor in series with that result and go from there. So if this looks similar to how this was done for capacitors, it's very similar. It's almost the same kind of process. So let's go ahead and redraw the picture. So we'll leave resistor 1 alone to start with. So I'll have that. But now let's imagine we take these two resistors, combine them together to form a brand new resistor. So this is an imaginary resistor, but to be fair, the whole problem's imaginary, so it doesn't matter too much. But we've taken these two resistors here, let's combine them to form this resistor here. So that means we need to calculate what the value of resistor 4 is, if you will. Because these are in parallel, the formula for resistors combined in parallel is the reciprocal formula. And in this particular application, looks like this. All right, so let's go ahead and write down what the results are. So 1 over R4 is equal to 1 over 16 ohms plus 1 over 20 ohms. And when we do this carefully, we'll find an answer of 8.88 ohms, like that. Okay. Now, again, when you do these kinds of calculations for parallel resistors, you want to make sure that first you add up these carefully, but then note that this is 1 divided by your effective resistance, and you need to take the reciprocal of this number here to get that. So watch yourself carefully. Notice, as a habit, I carry along the units. So this is a hint. 1 over 16 ohms, 1 over 20 ohms. That's on bottom. If you want a resistance, the ohms have to be on top, right? So that helps you understand why we do what we do. Okay, we've done this before, so I'm not going to belabor the point. Okay, so next step is to find the combined resistance of these two. These two are in series with each other. That will make this calculation a lot easier. We'll call that the effective resistance for the entire circuit in this particular example, and that's just R1 plus R4. R1 is 24 ohms, and we have this 8.8 repeating ohms for R4, and 32.8 repeating ohms then, if you will, for the total. So there's our effective resistance for the entire circuit. If you prefer to round it off to 32.9 ohms, it wouldn't say nay to you, but I'm going to keep it like this because when I do these problems, especially when we get numbers that are a little crazy like this, I want to be as precise as possible. I want to keep the maximum amount of precision I'm allowed to pick. So while you can round off for an answer like this, that's fine. We want to make sure we use the most possible precise answer when we're taking it forward into new calculations. So with that in mind, let's do a new calculation. So what is the current then through the battery? Now, to remind you of how this works, we're imagining we have one resistor that replaced all three of these, which we call the effective resistor. Notice I don't say total resistor because it's not the total, right? It isn't 24 plus 16 plus 20, is it? It's some other number. So effective resistance, what does this imaginary resistor effectively do? Okay, that's why we have the name for that. We'll take the 12 volts for this particular battery, divide by this 30.888 ohms, if you will. And when that gets done, we end up with a current of 0.365 amps, like that. Okay, so now I'm going to go ahead and extend the significant figures out to a third digit, and I'm doing that because I'm looking ahead a little bit. I want to see and make sure that things, again, work out the way they do. Now, if you were reporting this as a final answer, I only have two significant digits over here, then you'd round off to, say, 0.37. So if your instructors want to be sticklers for that, you would end up doing that. But here I'm going to play a little bit loose with the sig figs because I'm looking ahead and I want to get a proper answer for this. So that's the current through the battery, if you will. All right, what comes next? Okay, well, let's quickly redraw our pictures, but in reverse orders. So we have an effective resistor circuit like that. We have determined, or we were given, a potential difference of 12 volts. We have a effective resistance of 32.8 repeating ohms, and that gave us a current of 0.365 amps. So that's what we had there. Now, if we back up the pictures, if we reverse gears, so to speak, the previous picture looked like this. We had R1 and R4, like that. Now, this is something else we've discussed before. Current is a flow of charge. What that means is that you don't divide or cut up the charges or the current between, say, here and here. That might be a temptation to do that, but you don't do that. Because current is a flow, it has to flow through everybody in a circuit. And if you're along the same path, you go. So if there's, say, 10 cars driving down a 2-lane highway and suddenly there's construction and only one lane is open, those 10 cars still have to go through that one lane, right? It doesn't matter. So the amount of current is like traffic flow in that analogy. So that means the calculation is not even necessary for this resistor. I1 equals that current, 0.365 amps, like that. Now, why did I just focus on I1, the current through resistor 1? Because that's one of our original resistors, isn't it? What I want to do next is talk about the current through each of the resistors that created this. So let's again go backwards with our picture, redraw it, if you will. And this, by the way, is a good technique for working complicated circuit diagrams like what we're showing here, is to go forward, for example, into getting to your effective resistance, and then go backwards to find out the currents through each of the individual resistors. So we're going backwards through our pictures. All right, so now the current, which is 0.365 amps, comes through here, reaches this junction. Has two choices, if you will. The current can either go through this resistor, R2, or the current could go down here through the resistor R3. So in this case, the current is going to split up between two different sections. One more thing to remember, the larger the resistance, the less the current. The smaller resistance, the more current. So just to remind ourselves of what these numbers are, R2 was 16 ohms, R3 is 20 ohms. So whatever else happens, R2 is a smaller resistor, there should be more current through it. R3 is a larger resistor, there should be less current through it in comparison. And one more thing to check on, the totals. R2's current, R2 we'll call it, and the current through R3, which we call I3, the currents here should add up to be the total, exactly the same as the current through this. So we've done this in a previous video, so I'm going to go a little bit faster through this, but I2 then equals the ratio of R3 over R2 plus R3 multiplied by this current. Again, because resistance and current are sort of inverse ideas here, I'm not using R2, I'm using R3 here, okay? So R3 is 20 ohms. The total of R2 plus R3 is 16 plus 20, like that. And we just found it was 0.365 amps earlier, like that. We go ahead and do some calculations. And what we find is that I2 is 0.203 amps. Now, as always, I suggest you do this. If you're following along, it would always be a good idea to pause the video or at some point do this. Run these numbers yourself. Don't take my word for it. After all, I'm human as like everybody else. I can make mistakes or I can forget to write something correctly. Always run the numbers yourselves. Check and make sure it works. Also, just as a side benefit, when you practice this way, then that helps you remember how it's done, and that might be of advantage for you, say, during exam time. So I advise, don't just take my word for it. Try it yourself, make sure it works. All right, how about the current through resistor 3? We'll call that I3. Same logic, it's R2 over the total of R2 plus R3. Same logic, okay? That's 16 ohms over 16 plus 20. And again, 0.365 amps off to the side like that. Again, just to shorten things up, I'll cite the answer. That was 0.162 amps. Now, one last check on the current situation. I did not mean to make that a pun. The total current should equal the currents in each of these individual resistors. So let's write it out. Is it true? 0.365 amps. Does that in fact equal 0.203 plus 0.162? And if you look carefully, yes, it does. So that makes sense. Now, by the way, you could have gotten, say, this answer much more quickly once you had that answer, right? Because all you had to do was subtract and you could get it. So we know it's supposed to be that. But it's always good to sort of double check, to go through the process and make sure that, yes, you are getting the answers you expect to get. Okay, so those are the currents through each individual resistor and the current through the entire circuit, or shall we say the battery. Okay. Now, last step is to take a look at the power output. So let's do that. It makes for scintillating video to watch me ripping paper, I know. So, in the case of power, the power that is given, or the power is gained by the circuit, is equal to the current through the battery multiplied by the voltage delivered by the battery, right? So, what was that number? The current was 0.365 amps and 12 volts, like that. And the number that we achieve is 4.378 watts. So that's the power that's delivered by the battery to all three resistors, okay? Now, here's what we want to check. Let's calculate the power in each of the resistors that's used by each resistor and compare that to this power we've just calculated here. If you've been following along with these kinds of discussions, both here and in your lectures, we know what to expect to happen in general rules, but we need to show it. So, the power that's used by resistor 1, I'll call P1. That formula is not I squared or IV, it's I squared R. And it's because it's specifically the current in I1 and the resistor R1, we need to write it like that. So, the current through resistor 1 was the same as that current, so it's 0.365 amps. Squared it, notice, it's not just that, but it's squared, that's important. And the resistance was 24 ohms. So, do some calculating, and again, liberally taking significant figures here to show off what I want to show. I get this number of watts. Notice it's not the same. That's, if you think about it, that's simply because there's more power to be used by the next two resistors, aren't there? We haven't finished with the other resistors. P2, the power that's used by resistor 2, is then I2 squared multiplied by R2, like that. I always have a desire to say R2D2, but of course it's got nothing to do with this here. All right, so it was 0.203 amps squared, and that resistance was 16 ohms, and 0.657 watts is the number I got there. I should say, by the way, that I was very careful in doing these calculations. I'm writing it to these numbers significant figures, but in fact, when I did my calculations, I actually used the ratios to make sure I kept all possible digits. That's a thing that is worth doing sometimes. Use all the possible numbers that you have to make the calculations. You do the rounding off at the end. When you come to the final results that you cite, then you can round everything off. In other words, don't round off too early. You'll cut off some information that you otherwise can use. All right, if you look carefully at these two numbers, this plus this, that's not quite equal to that yet. Let's do one more, and that's resistor 3. So the power in resistor 3 is I3 squared R3. Now I3 had a current that was, let's see here, 0.162. And the resistance was 20 ohms in that case. And when that was done, it was 0.526 watts. So here's the thing that you can check at home. Is this total power here that we said that was gained or given to the circuit equal to the power used by each of the three resistors, the sum of those powers? If you've been paying attention, conservation of energy applied to circuits suggests that yes, this should be here. But check and see, is this number equal to this plus this plus this? And I'm going to leave it at that. All right, so funding for these programs comes from the University of Mississippi and University of Southern Mississippi. Our technical support staff is Sydney Gautraw and Sophia Turner. The videos themselves are filmed in Hattiesburg, Mississippi. I am your host, Dr. Christopher Cirola. Thanks for your attention, everybody, and clear skies.